Yeah, so I'm Michael Hackney. A couple of slides here to set things up. Railcom has been in the railroad technology space for coming up on 17 years. Actually, I think we just had our 17th anniversary. And our primary focus is around yard automation, computer-aided dispatching, and then when I came on board last year, really moving into smart monitoring and analytics, and that's what I'm going to talk about today. I've got a few slides, maybe about half my presentation, to kind of set up the problem here at the beginning, a problem statement, kind of the things in the railroad space that we're interested in, some of the challenges, because the railroads are kind of a unique application, and then get into the beef of things and end up with a case study and show you how we used automated predictive analytics from falconry to really help streamline what we're trying to do. So the problem at the end of the day is all around predictability. Railroads depend on predictable operation of their trains. And in fact, if you go into the boardrooms, they measure predictability by delay. Or the freight railroads use the term velocity, but it basically is measuring of delay. Delays cost money. They create negative customer sentiment. So here you can see our Boston Metro. All the trains are delayed and all the passengers are getting upset. Safety and security concerns. One thing, if you think about it, maybe you don't know this, but trains carry a lot of nasty things. Chemicals, in this case, radioactive waste, and they go through metropolitan areas. So if you have a failure due to equipment, a locomotive or maybe even a switch on the track fail, and you're carrying a bunch of nuclear waste through Philadelphia, that is a big security concern, and that actually happens. And here we have armed guards watching that train until they get the problem fixed. And of course, the last element is that by their nature, they're unpredictable. There are really two broad categories of things in railroading. We have the rolling stock, the locomotives, the cars, and equipment that's on board, primarily the locomotive. And Railcom is not in this space. The manufacturers, the GEs and all the other locomotive manufacturers put a lot of technology into these locomotives, for safety, for fuel efficiency, for all kinds of things. So they are highly instrumented. The cars behind that locomotive, though, are at the opposite end of the spectrum. They're basically not instrumented. They're kind of, big boxes with wheels. And they're too expensive to actually instrument each of the individual cars. So a lot of what are called wayside equipment or wayside infrastructure monitors that look at the wheel bearings in the cars as they go by to detect if they're hot, which means that there's a bearing failure imminent, or maybe the bearing has failed, which ultimately ends up destroying the track if you run the train with a locked up wheel over it. So a lot of wayside equipment that monitors not only the cars that are moving by, but also control the direction of the train, the switches, signaling devices, and a bunch of other types of technologies. And it's the wayside equipment that we're focused on. So some of the challenges, if you think about it, railroads run through severe weather. This is up in Canada Pacific, through basically a tunnel of 15 feet deep snow that they had to tunnel through, all the way down to, the equator where it gets very, very hot, deserts, all kinds of environmental conditions. Remote locations, here we have a train going across the Midwest, and these locations have basically no communication infrastructure except for satellite. They may be 50, 100 miles away from the nearest human. To highly populated areas, and we saw one of the challenges of highly populated areas with a breakdown of a train that was carrying radioactive waste, but you have delays if a train breaks down, or even one of these crossing gates. If that breaks down during rush hour, believe me, people start calling their local townsmen and whatnot to get that resolved. Create challenges both remote and populated. And then the biggie is antiquated technology, and we'll talk a little bit more about that here coming up. It's basically electromechanical technology that's pretty unsophisticated. And really what it's all about is maintenance. How do you keep electromechanical equipment up and operating? You go out and you try to be as proactive with maintenance as you can, because at the end of the day, the goal is to completely eliminate faults, right? If you have a fault and you have to go out and do corrective maintenance, you're being reactive and it's extremely expensive. Trains are stopped, cargo may be refrigerated, is getting warm and is going to decompose. If it's stopped at a railroad crossing, passengers and drivers are getting really upset. And the way that's typically done is through proactive scheduled maintenance. And in fact, it's government mandated because there are safety, security issues. The government mandates scheduled maintenance for the railroads. More recently, they've been moving into condition-based maintenance, and we'll talk a little bit about that. And then what we're trying to do, which is expensive, not as much as scheduled, but a little more expensive. And then what we're trying to do is move into predictive maintenance. So you're optimally right here, where you're spending the least amount of money to figure out when a problem is going to occur so you can fix it before you end up at this point, or it's too late. So let's talk a little bit about condition-based and predictive maintenance. I've found in the railroad industry in particular, maybe you've experienced this in your industries, that there's a little bit of FUD. People don't understand the difference between condition-based and predictive maintenance. Condition-based is really sort of static. It's looking at the current state of the equipment. In this case, maybe there was a snowstorm or ice storm, the switches are iced up. That's the current condition, you go fix it. It's analogous to a pilot going out and walking around the airplane before it takes off, looking at the plane, saying, hey, everything's okay, get in and take off. Predictive maintenance actually looks at data that's collected of in this case, railroad equipment, and condition monitoring, and applies analytics to it, maybe brings in multiple data sources, weather data, other data sources on operations, and puts together sort of a prediction of when that equipment may fail. So you can actually be proactive. This is an interesting case. This is from our product where you actually see the current decreasing over a period of time, and you might say, aha, it looks like it might fail out here, so we should probably go and repair it. It turns out this is a seasonality effect over the course of the year. It gets colder in the winter. The switches actually take more current to throw. And so by combining the weather data, we know that, and we don't have to send a maintainer out to fix the switch because it actually isn't going to fail. It's going to go back up. So you can get a lot of value out of the analytics. Okay, and sort of this is what we're dealing with. In the old days, the old way, we're talking mostly mechanical devices or simple electromechanical devices. This is a switch. There are still thousands of these in operation in the United States where someone physically has to go there, throw the switch so the train can switch tracks, and then throw it back. They're opaque mechanical or electromechanical devices, obviously no sensors, not much in the way of data networks or communications, not much in the way of data, and any analytics might be simple reports, descriptive analytics. More recently, we have very expensive, really over-engineered sort of sensor technology, and this is primarily because of that harsh environment that the railroads run in. And so the railroads put really high levels of requirements on the environmental elements of the sensors. So they have to be really over-engineered, consequently they're very expensive. But there are more and more of these that are coming into play. The networks are getting better, but there are still thousands and thousands of miles of railroad that don't have good data communication, reliable data communication, so you can't count on it. And now we're starting to get into operational log data and some diagnostic analytics, right? Condition monitoring and condition-based maintenance. Where this is moving to in the future is ubiquitous, low-cost sensors. And the sensors, the devices themselves has a sensor technology built into it. So you can imagine a switch machine that actually has the sensors built in. So you plug it into the network. We're talking about real-time, high bandwidth, ubiquitous network. And we're talking about multiple data sources that's going to contribute to a data explosion. So not only in this case, a switch machine, but we've got the weather data that you're bringing in. You might have data about the track and expansion of the track and gaps in the track and all kinds of things, and we can bring all of that in, feed it into our analytics, and move now into a world of predictive analytics, and then sort of our goal in the future is around prescriptive analytics. So how do you get the best out of what you have? Okay, and they're really, the technical side of things, I think we have a pretty good handle on. The real challenge now is they're twofold. I'll start with the one on the right. And you'll see this in our case study, is when we develop our analytics for a new device that we want to monitor, basically it requires a lot of data up front. It requires some pretty sophisticated data scientists to develop the analytics for it. And it's not static. You have to continue to make an investment in the data scientists because you'll discover new things in the data. as you collect it over time. And that's sort of the needle in the haystack phenomenon. As you'll see in our application, we've identified a number of conditions, but we know that there are other conditions out there that might have a long mean time between failure. We just haven't seen them yet in this particular situation. And unless we continue to monitor manually and have our data scientists look at it and develop analytics for it, we might miss it, and that would be bad. So, transforming what is really an iron age, because it's the iron horse, right, the train industry, it really comes down to a cost versus benefit. I mentioned earlier that the railroads use the metric of velocity or delay, and they actually put a cost to that number. Most railroads have a pretty realistic cost that might be in the neighborhood of a couple of $1,000s an hour, a couple of thousands of dollars per hour for a delay. So if you had a delay for an hour, basically it's going to affect your bottom line by $2,000. But there are still some railroads out there that have really ridiculously low cost per hour of delay that really only takes into account the amount of fuel that's being consumed while the train is sitting on the track not moving, and the payroll for the crew of the train, and nothing else. They don't look at the downstream network effects and all of the other, their fines that can be imposed upon the railroad, not only by their customers, but by the government in the case of Amtrak and passenger rails. And so what we need to do is build cases and technology that can be cost effective to solve these problems within the constraints of the cost of a delay. Explosive data growth, as we start to put more sensors out there, it becomes more and more data that we have to deal with, and that's a challenge. And then the last one, and what I'm going to be talking about with our case study and the use of the falconry technology, is all around the way we've done it initially was using brute force analytics. And that comes back to the previous slide about having to bring in data scientists for every new device type we want to bring on board, and then knowing that there are going to be other types of failure modes that we may not see during the development of the analytics brute force wise. So it's a big challenge, and the good news is there's a good answer for that. So now I'm going to shift gears a little bit and get into the case study and sort of what we're doing. So Insight is our predictive analytics platform, and the first application we brought to market in September of last year on that platform is for mainline switches. And I have a picture on the next page of what a mainline switch looks like, but Insight sits up in the cloud. It's gathering sensor data from out in the field, in this case switch throw waveform data, current draw data. It's combining that with weather data and other data sources, and doing its magic analytics, and I'll talk a little bit about that up in the cloud. And then if it finds anomalies, it basically puts a severity level on them and then sends out a message. We can send text messages, emails, make a voice call, or use a simple network management protocol to alert individuals that there's a problem. But we also have an exploratory dashboard that you can go, and you can't really see it, but they're little graphical lights that go red, yellow, green, blue to indicate what the status of that particular location is. So it makes it very easy to navigate visually or to be proactively notified. And this is what a switch machine looks like. That's the device down here. It's electromechanical. There's a motor in it that basically pushes on some bars that are connected to this track section here that move back and forth. And that's all it does, is move back and forth to move a train down this path or down that path. And what we're actually doing is very simple. Current clamp around the cable that goes to the motor and measuring the current. And we get out of it a waveform that looks like this. So this is current over here. That's about 25 amps. And this is time. And we're talking about 12 seconds. Some switches throw fast, 4 seconds. Some might take 12, 15 seconds. But this is kind of representative of what one of these waveforms look like. And there are really 4 segments to it. There's a current inrush. So this is when you push the button to throw the switch, current inrushes, and you see a spike. Then there's an unlock phase. These switch machines have safety mechanisms built into them to lock them into place. So when a train goes over, it doesn't move and derail the train. So you have to unlock. Then the switch actually throws, so that's the movement, and then at the end it locks again. And so you get a waveform that looks like something like this. And the whole thing is that when there's a problem or a developing problem, this waveform is a fingerprint. We'll actually see patterns develop in this waveform that you can then analyze and either alert that there's a problem right now or there's a developing problem. I'll mention a couple of those here in a minute, actually on this slide. So the kinds of things that we're able to see by looking at the waveforms are battery issues. So as the batteries start to wear, they can't provide enough current. We'll actually see a decrease in the inrush current. Motor issues, problems with the brushes in the motor, similar sorts of things, drawing more current. Lock rod issues, they start to wear or they get knocked out of place when trains run over them or just through a thermal expansion contraction, snow and ice buildup. Ballast conditions and excess friction due to thermal expansion and other track movement. Those are all patterns that we have actually seen in the proof of concept that we did with 2 major Class 1 railroads. But we know there are other problems that these switches, other failure modes these switch machines could have. We just haven't seen them yet because of the long mean time between failure of those failure modes. The way that we went about developing this application was, basically we had to start with a lot of data. Around 25,000 switch throws, just to have enough data to look at, to start to look for, and when I say look for, I mean literally manually individual people looking at the data and looking for those patterns in the fingerprint, continuously reviewing the wave throw data. When we discovered an anomaly, we would have to call the railroad, the maintainer at the railroad, and say, hey, Bill, on February the 5th, we saw that there was a problem. It looks like it was a current inrush problem. What did you have to do to the switch that day? And he said, oh yeah, the batteries were dying, so we went out and replaced the batteries. So now we have a way of correlating the condition that we manually observed to what the problem is, and then we codify that in the application and develop, basically that becomes the analytics for the application, and then you have to repeat this. Every time a new waveform comes in, we have to analyze it. If we see anything new, we have to develop the code to actually do perform the analytics for us, factor it back into the application, and you just keep going. Of course, the problem with that is it's not very scalable. It requires a lot of data scientists. It requires a lot of data, and it requires a lot of time. Onboarding new device types, we mentioned that we're doing switch machines, but we've got a list of about 9 other devices that we are starting to develop analytics for. So each one of those new devices, we have to go through that same arduous, painful process. And it requires a high touch with the customer. We have to be constantly in connection with the customer. Not that that's a bad thing, but in this case, you want to try to do as much as you can without interrupting the customer, in this case, the maintainer. And the biggie is it's difficult to find all the conditions, and fine-tuning prediction rates is really tricky. And this was an interesting one when I came on board. I would have thought the goal would have been to have the highest prediction rate possible, but that's not the case in the railroads. They want a low false prediction rate. In fact, they're willing to sacrifice high prediction rate for low false prediction rates. False predictions mean that they actually have to send people out into the field, might be hundreds of miles away, out in the remote areas, at 3 o'clock in the morning on a Sunday morning during a blizzard, just to find out there actually wasn't a problem. So false detection is bad. So we want to minimize that. Okay, compare that to what we've done with falconry. So we built the application and realized these challenges and problems, and actually had started the discussion with falconry when we were developing that because we knew we needed to have a better solution. And the way it works now is we basically can start with a very small data set, start to feed it into falconry, and it's completely self-learning. No data scientists involved. It's an interface from our application into the falconry cloud service, and it identifies all the conditions. It doesn't know what those conditions are, obviously, but it can identify them. We then can correlate those conditions. Again, we have to go back to the customer and correlate that with what the actual problem was, a lock rod failure, obstruction in the track, whatever it happens to be. But that's a pretty simple thing to do, and we can even imagine starting to automate that a bit in the future, where we actually put on a mobile device in the maintainer's hands the application, so when we see a new condition, we can proactively ask, hey, maintainer, this is new, what do you think it is? And he can type in what it is, and maybe it goes through a review process and becomes part of the application. So even that can be greatly streamlined. Oops, and basically, you're done. That's it. There's not that continual iteration that we saw before, and it doesn't require a lot of people, and we can onboard new devices very quickly. So it's highly scalable, it's completely automated, self-learning, no data scientists, and the more data you throw at it, the better and better the analytics get. And we know in the future we'll see new failure modes that we haven't observed yet, so we'll get those new conditions and we'll correlate them to actual physical events, and we'll be good to go. And so consequently, onboarding the new devices that we want to bring on is going to be much quicker. And I just mentioned this, finding difficult or impossible to find things is going to be very possible. So sort of in summary, the brute force sort of old way of doing things was start with a lot of data, have a bunch of really smart people look at that data, try to correlate what you see to actual physical events, develop the software to codify that, and then just repeat over and over and over again. Never stops. Not scalable, costs a lot, lots of data, difficult to get right. Now with automated predictive analytics like Falconry, you connect a data source, you review the results you get out of that, annotate it with your domain knowledge, and you're done. Highly scalable, very cost effective, quick to onboard new devices. I mean, it took us 9 months to develop the analytics and collect the data to do that switch monitoring application. We've already done a quick and dirty proof of concept with a different device altogether. Very small data set, I think it was about 10,000 points of data. It wasn't complex waveform data, it was a different type of data. And within a day, we were able to see conditions in that data that would have taken us months to find manually. In fact, we'd had the data in our development group for probably 3 months, and no one had the time to look at it. So when we sent it through Falconry, we saw all the conditions, and now we start to put labels on what those conditions are, and we'll embody that into the application. And so that's it. Thank you very much.